Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at the very important Taylor's theorem. It will be, as we will see, this is a generalization of the fundamental theorem of calculus. And let us recall all that we need for this lecture. So what we have is, basically we'll need integration by parts. So the statement is that suppose we have two continuously differentiable functions, then this funny looking integral can be expressed that way. This is just a direct application of chain rule, and since this is somewhat of a unwieldy expression, we develop a notation which is standard, which is that suppose we have any function defined on, let's say, a closed interval, then we write this or that to mean this difference, where alpha and beta are points in the domain of f. So with that notation, this thing can be expressed either this way or that way. So much more compact than this guy. All right, these are the problems. We will make use of these problems today. Especially, this is just a very simple derivative calculation, and this will make sense once, in the course of the proof, it will be useful to take note of this problem. But anyway, I never recommend skipping any of the problems I give. So anyway, and as a side note, this can be written as that. So this will also be important. This simple note will be important to follow the proof. Okay, so we need some definitions. So suppose we have some function, then we call it continuously differentiable. I'm just recalling the definition of continuously differentiable function, which is that f is differentiable and its derivative is continuous. So that's the definition of a continuously differentiable function. And now we define for a non-negative integer, or rather a positive integer k, the notion of a k times differentiable function, which says that first of all f is differentiable and its derivative is k minus 1 times differentiable. So it is an inductive definition. For instance, suppose you want to know what is meant by a 2 times differentiable function or a twice differentiable function. It just means that f first of all is differentiable and its derivative is differentiable. 1 times differentiable is same as saying differentiable. So 2 times differentiable function is f is differentiable and its derivative is also differentiable. Similarly, 3 times, 4 times, and that is neatly expressed in this inductive fashion. Convention is that every function is 0 times differentiable. So that's a convention. And now for the notation, suppose we have a k times differentiable function, then this is the kth derivative of f, which is defined as this. So it is the derivative of the corresponding k minus 1 guy. So this is also an inductive definition. So if k were equals to 2, then this would mean that, but this notation is same as the derivative of f. So this is the derivative of the derivative. So that's what it means. So f of 0 is f. This is our convention. And with that, you can just deduce everything. So if k were equal to 1, then here you would see just f. So f, and with that bracket 1 written above f, would mean the derivative of f, which is what we used here. So this is an inductive definition, and you can figure out what all of these means. Basically, this is the kth derivative of f. All right, this is also the same thing that I've expressed in a different way. Lastly, we need this definition that we have a function and we call it a ck function if it is k times differentiable and the kth derivative is continuous. So a continuously differentiable function is precisely a C1 function, as I had written here. Okay, so with these definitions, let us move ahead and state and prove Taylor's theorem. So here is a wordy looking statement. What we have is a ck plus 1 function, meaning a function which is k plus 1 times differentiable and its k plus 1th derivative is continuous. K is some non-negative integer. Okay, and you fix any point in this interval I on which the function is defined, and this I is an open interval. Then f can be broken into two parts, the polynomial part and the remainder part. The polynomial part is this, And this is indeed a polynomial. These are all numbers. This is a number, and these are, well, exponents of some shifts of x. So all of these are polynomials. So basically pkx is a polynomial. And this remainder is this horrible looking thing. And this may make no sense at first glance. But to understand this, let us take a particular value of k, which is the simplest one, k equals 0. Then if you just work it out, you will see that the polynomial part is just this constant. And the remainder part, if you substitute k equals 0, this becomes a 1. This is x minus a, as I've written here. This goes away, k is equal to 0, this goes away. This is just the derivative of f, and this I have repeated as such. So we get that, and therefore fx is p0 by the theorem. I'm using Taylor's theorem now. So p0 is fa, so fx is p0 plus r0. Therefore this difference is that thing. And here is basically where we use this exercise. So if you use that exercise, you will get this guy, which, so we get that as our, the Taylor's theorem for k equals 0 says just this. So this is of course the fundamental theorem of calculus, or a consequence of the fundamental theorem of calculus. So what we see is that for k equals 0, Taylor's theorem just regurgitates the fundamental theorem of calculus. Therefore, it is a generalization of the fundamental theorem of calculus. So you can think of this as, you should interpret this in that fashion. Anyway, so let me just give a proof. Despite the apparent complexity of the statement of the theorem, the proof is not going to be very complex. It is, in some sense, a mindless application of this thing by parts, integration by parts. But the only way I can convince you of that is by actually giving a proof. Saying it is not going to cut it. So, all right. Given this statement for continuously differentiable functions, so k is equal to 0 is settled, and we will do by induction. So assume the theorem holds for some k. Holds for some k. We will prove for k plus 1. So we want to show that. F is pk plus 1 plus rk plus 1. So where we assuming f is f is ck plus 2 function. Why ck plus 2? Because for k, the statement is that for a ck plus 1 function, blah blah happens. For k plus 1, the statement would be for a ck plus 2 function, pk plus 1, rk plus 1 is the decomposition of f. So this is what we want to show, assuming f is ck plus 2. Okay, so the thing is that, well, we will show that rk can be dealt with using integration by parts, and the main thing to deal with is the integrand. So we define it separately. So let me call this I of x. This whole thing is I of x. Or rather, I need a subscript. So this is I sub k of x. Okay. So we will apply the by part rule. Fine. So assume f is ck plus 2. And since ck plus 2 is clearly ck plus 1 also, therefore f is pk plus rk by induction hypothesis, because we have assumed the theorem holds for k, and hence whenever we pick a ck plus 1 function, We have picked a ck plus 2 function, but ck plus 2 function is a ck plus 1 function also. Therefore, we can write it this way. And now we will deal with this ix guy. So ikx, as we defined, is this integral 1 minus t to the power k, the k plus 1 its derivative, a plus t times x minus a dt. So to apply by parts, we need to fix an f and a g. So this is going to be g prime t. So g is such that this is g prime t and this is ft. So now look at the second problem. If I fix my g prime t to be that, then gt has to be this. So fine, we apply by parts with the notation that we recalled it. So the notation of by parts that we have is this. In this notation, we apply by parts. So what we get is, the first thing should be, here we should get ftgt from t equals 0 to t equals 1. So what is ftgt? Ftgt is minus 1 minus t to the power k plus 1 divided by k plus 1. That is gt. Ft is as written above. And this is from t equals 0 to t equals 1. And minus integral 0 to 1. Here I'll have a gt, which is minus 1 minus t k plus 1 upon k plus 1. And now f prime t. So for f prime t, I'm going to write this, this is a notation which we have never used, but let me use it today because I'm sure this is familiar from high school. So this is basically, all I'm saying is this is f prime t. This is my way of writing f prime t, at least for this lecture. I could have just written f prime t also. Maybe that was a better idea. Anyway, so what is this expression? What is this first guy evaluating to? At t equals 1, this gets killed. So this is 0. At t equals 0, what happens? At t is equal to 0, we get minus 1 upon k plus 1. And here we will get f k plus 1 at the derivative at a. Fine. And this minus becomes a plus. Integral 0 to 1. Let me take the k plus 1 out. So this is integral 0 to 1. 1 minus t to the power k plus 1. And this derivative, if you apply the chain rule, you will get an x minus a will pop out. And you get this. So this x minus a I really want to take here, and let me do it. So I take it and put it here, and I adjust the expressions. All right, a lot of time saved. Fine. So let me just check if there is any calculation mistake. No, I don't think there is. Yeah, there is one calculation mistake. This is actually, this minus sign is not there. This is a plus. Because this means that you evaluate this at 1. Oh, sorry, this whole thing. Evaluate this whole thing at 1. Evaluate this whole thing at 0 and take the difference. So when you take the difference, this minus becomes a plus. So, okay, we have that. And now, what is RK? So this is the expression for IK. RK was basically x minus a k plus 1 upon k factorial times ik. So therefore this gives us, by the calculation above, this thing will get multiplied by that to give x minus a to the power k plus 1 upon k plus 1 factorial times the k plus 1 is the derivative of f at a, plus this thing gets hit by that to give us x minus a to the power k plus 2 upon k plus 1 factorial integral 0 to 1 minus t k plus 1 this should be again, so yeah, this is a 2, sorry about that. This is k plus 2. That was a typo. A plus tx minus a dt. Okay. So we have this, and now, of course, this is our k plus 1. So this is equal to so therefore pkx plus rkx is pkx plus x minus a k plus 1 upon k plus 1 factorial fk plus 1a plus rk plus 1x. What did I do? I just substituted this above thing in place of rk and got that. And the observation is that this thing is pk plus 1. So you can verify the expression of pk plus 1 was given above. So you can verify. Now let me, I should have mentioned this earlier. Everything here is making sense because of our assumption that f is ck plus 1. If f is a ck plus 1 function, this integral makes sense because this is a continuous function and this is a continuous function. So if we multiply two continuous function, we get a continuous function, and hence we can integrate it. Every continuous function is integrable. So therefore we need this hypothesis of ck plus 1. And if you have ck plus 2, similarly all of these integrals then start making sense. So that is the point of the hypothesis. Alright, so we have proven the Taylor's theorem now. This induction is complete. So this proves Taylor's theorem. So this is just one form of Taylor's theorem. Next time we will look at another form of Taylor's theorem, which we will deduce using this form. So with that, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.